Hi, I'm Bart Stock. We're going to be talking today about science in the microcosm and the macrocosm. And I'm just going to put up something here for people to see. Give me a second. Okay. So here we have it. On the left, we have the macrocosm. Have a picture of a galaxy. I believe it's the Andromeda galaxy, the galaxy that's closest to our Milky Way galaxy, but it's still billions of light years away. And on the right, we have the microcosm, a graphic showing what physics calls the standard model as of 1975. This displays all the different particles or if you will, fermions and bosons, as well as things like neutrinos that make up the piece parts of everything around us. And we're going to deal with both of these in this talk and expand on them. Now, the purpose for this is to really go through the two ways you can live your life. One is as though nothing's a miracle. The other is though everything is a miracle. And when I look out the window, I see this incredible diversity of nature. And as we saw, when you look down in the microcosm or up in the macrocosm, that's a totally different set of order. That's just amazing. So continue to be amazed as we look at the miracle of the universe around us. What is the problem here that we're dealing with? Well, after 500 years, Western science realized it's been studying 5% of the mass and energy in the universe. The remaining 95% is called dark. It's 27% is dark matter, 68% is dark energy. So this is not a minor miss. This is pretty huge. And the best and the brightest are working like crazy trying to figure out how to resolve this. So one potential solution to this problem is to hypothesize there are more dimensions than just 3 spatial dimensions, so that the remaining dark matter and energy can reside in these other dimensions. So let's just take a look at this. If 5% is 1/20th of the matter energy in the universe in 3 dimensions, then we need 60 dimensions to hold everything. So is this the right number? But the point is it's much more than 3. So we're going to pursue this idea. How in the world would we get these extra dimensions? Well, we live in 3 spatial dimensions and one, what people call time, a temporal dimension, and these 4 together, 3 space and 1 time, make up what is called spacetime. So one way to conceive of these extra dimensions then is to rotate something perpendicularly in your mind by 90 degrees away from an existing dimension. So if we start with the x-axis, which I've shown here up in the top right, this horizontal line is an x-axis, and it's labeled real. And then we rotate 90 degrees up to this perpendicular to it, which we'd call the y-axis. Then if we rotated 90 degrees from the y-axis, we'd get a z-axis. So let's take a look at this a little more. We've got time. The problem is the units for time are seconds. So we're going to multiply time by the speed of light, 3 times 10 to the 8th meters per second, so that now the units of speed of light times time are length, they're meters, just like the dimensions that we have in the 3 spatial dimensions. Then finally, we're going to do this rotation by multiplying by a square root of -1. So what happens here, if you can see in this picture here, is by taking something that goes out here, say to the 0.1 on this real axis, and rotating it up 90 degrees, we're now perpendicular. We're lying on an axis that's perpendicular to this one simply by a multiplication by the square root of -1. And there's some trigonometry here that tries to explain this. So the natural dimensions of space-time appear to be the three spatial dimensions, x, y, z, and then the square root of -1, I, times c times t. So there you go. So that's where we're at. We're in this four-dimensional space-time. And then what happens here, the reason why we need these extra dimensions is all started with dark matter, which was discovered by astronomers looking at rotating galaxies. The telescopes finally got good enough in the 1920s, 1930s onwards, so that they could see that what they saw were nebulae, that is, blurs that they assumed were stars, were actually galaxies. The galaxies appeared to, many of them, to be rotating, as shown in the picture up here. And so people plugged in estimates. They said, let's assume we have 1 billion stars here, and they each have the mass of the sun, our star, and that they're all attracting to one another by gravity. So if you assume that and let the thing spin, then you would quickly discover that what you saw as this galaxy would spin apart unless there was additional matter, dark matter you can't see, that's contained in here, that is going to gravitationally bind all the stars together. So since the dark matter interacts by gravitation with matter, that suggests that they're in some sense quite close to one another, because gravitation is a relatively weak force. So where in the world would this dark matter be? Well, if we have matter in a four-dimensional space-time subspace, then we're going to take each of those, x, y, z, and ICT, and multiply by the square root of -1. That gives us another 4 dimensions that are all perpendicular to the 4 dimensions that we live in. So that means that the units here are ix, iy, iz, and now we have I squared times ct, but remember I is the square root of -1, so that's minus ct, or to put it differently, the space that we're talking about here is indeed perpendicular, but it appears that the notion of time might reside in our space, except that it's a part of time and therefore is different all by itself. It's not really a spatial dimension, even though we talk about it that way. So the 3 spatial dimensions for dark matter really are perpendicular to our 3 spatial dimensions for dark matter. So x is perpendicular to the dimension square root of -1 times x, y to square root of -1 times y, and z times the square root of -1 times z. And time, which involves ICT, and then also I times that, gives us something else which is perpendicular. They're each perpendicular to each other. So logically, it appears that this time dimension that involves matter, that this is ICT, and this is orthogonal to the time dimension for dark matter, which is minus CT. Just pursuing turning the crank here. Another thing that comes up here, though, is extra dimensions can be compactified. Where did this come from? Albert Einstein developed his equations of general relativity, and he started popularizing them in 1915 for space-time, 3 spatial dimensions and 1 temporal dimension. And this gave a brand new theory for how gravitation operates. That is, gravity is actually a curvature of space. The greater the amount of matter you have, the greater that it will curve space, and therefore things, if the curvature is great enough, you'll be attracted that much more strongly to it. So in 1919, Theodore Kaluza wrote a paper to Einstein, and he added another dimension to Einstein's formulation, and he noticed that in this now 5-dimensional treatment, he could obtain Maxwell's equations of electromagnetism. He could contain, there were another 4 potentials, vector potentials and scalar potentials, that themselves would lead to electric and magnetic fields. And Einstein looked at this. He couldn't see anything wrong with this. He just didn't know what to make of it. In 1926, the German mathematician Oscar Klein said, well, maybe this 5th dimension that he's talking about is compactified. So here, let's take an example of what he was talking about. Let's say that the compactified dimension is actually has 2, we're going to do 2 compactified dimensions, one running this way and one running that way. So effectively, this one here could be multiplied by the square root of -1 here, so that it's really one, if you will, complex dimension that we're dealing with. And if we take that and wrap it around, say, an x-axis that we have here, then if we look down the x-axis, really very, very deep, incredible magnification, we'd see that there's another dimension wrapped up around this x-axis, and that would be this compactified dimension that Klein came up with. Again, notice that he paired these things to come up with this. So let's follow through on this idea of compactified dimensions. There were a Congress of International Congress of Mathematicians where Eugenie Calabi announced a theorem, and he discovered that his proof of this theorem had a flaw, so it became a conjecture. It wasn't a proof, and the end result of this was that people tried to prove that it was true or it was false. So in the 1970s, the mathematician Yau began to work on this conjecture, and initially attempted to disprove it, but after several years of work, he realized it was true. He found a proof of the conjecture and was able to come up with several really striking consequences of its validity. Here is a picture here of a 6-dimensional, what's called Calabi-Yau manifold. There's another one down here, but these are done in 2 dimensions. So, and notice that these things have all kinds of colors, holes. They're moving all over the place if you actually looked at this, and so it goes. So the end result of this was that this is believed to be the basis for these extra dimensions that were found suggested by the experimental work that came up with dark matter, where it said there was extra matter and energy there, but it was in extra dimensions. So Ron Cowan worked on this. In very deep meditation, he came to realize that there actually are 26 dimensions. There's 10 dimensions for matter, 10 dimensions for dark matter, and there's 18 dimensions total that are compactified here. Here they all are. And that this leads to a 26-dimensional space. The thing to keep in mind here is that these things are paired. So there's a real and imaginary dimension here for the X, the Y, and the Z. That gives us 6 dimensions here, 6 here, and 6 here. And the end result is that we end up with matter living in this 10-dimensional space, dark matter in this other 10-dimensional space, and what we call photons or bosons operating in all 26 dimensions. An incredible set of observations. Ron also observed that there were holes in these Calabi-Yau manifolds. So there's a total of 8 holes in 18 dimensions. So really there's only 10 dimensions here, 10 real dimensions. Yeah, yes, there's 18, but the holes connect them together. And that by itself was amazing. And then the fact that we have 3 holes in the space for matter led to the observation, as we'll see, that there's a possibility of having 2 resonances for something like the electron. So the electron, because of these three holes, will have two other resonances for what we call the electron, but there's really only one electron. The resonances are due to the holes. And similarly, over here for dark matter has four holes. There'll be four resonances. And so it goes. So Ron did a lot of this by drawing on insights from the German mathematician Emmy Noether, who's shown here. So in this geometry of the universe now, the Calabi-Yau manifolds, as you can see, are all paired. So there's 6 real dimensions, but they're paired into 3 and then 3 perpendicular. Well, those are all multiplied by the square root of -1, and then so it goes for everything. Now we're not done. There's still more dimensions. What happened in chemistry was that there was a notion of a basic material, an atom, and the atoms became the basic components of things called elements. And we got to the 1860s, Mendeleev, among others, constructed a table of the elements, and they were arrayed in with an incredible amount of symmetry here. And the advantage of this was there were elements that had been discovered, but there were spots in the table for additional elements, and in fact, those were discovered as well. So this periodic table of elements was incredibly useful for suggesting what is truly basic and what makes up what we would call chemistry today. Now, starting in the 1830s and going up to the 2000 timeframe, thousands of mathematicians worked on looking at symmetries. Symmetries here are called finite simple groups, so they're rotations, they're translations, things like this. And they determined that they constructed a periodic table of symmetries. So there's 20 categories here, 20 major categories of symmetries, like I mentioned, like translations, rotations. So in a symmetry rotation, if I take something and go to the origin of the coordinate system and rotate around it, I can rotate all the way back to where I started from, and everything is completely symmetrical. Nothing has changed. That's just one example of what's going on here. So we have these 20 major categories, but there were another 26 categories that were called sporadic because they didn't fit into the 20. So in other words, the study of symmetry led to the discovery of asymmetry, of lack of symmetry. So there's 13 here and 13 here for what are called these sporadic symmetries, and that's 26. So what it appears going on here is that each of these sporadic ones is tied to one of these 26 dimensions in the universe, and it's not clear yet how this is, but it offers the possibility for each of those dimensions to be tied to one of these, and each of these by themselves involve, some of them involve thousands of dimensions. So there's a basic dimension, the 26 dimensions, and then there's literally thousands of other dimensions that are variations off of that we can reach from here. And there's a lot of evidence that suggests this is what's really going on. But much work still remains to be done. So additional things that Ron Cowan, in the 1990s onward, with heavy meditation, he took a look and realized that there really were 2 types of subquarks. You need 3 subquarks to make 1 quark, and 3 quarks to make either a proton or a neutron, different types of quarks for doing this. And he looked, for example, at the electron and realized the electron had 10 closed strings to it. And the 10 strings captured energy. They were resonant, they were vibrating like crazy, and they captured energy as like a jelly inside it. So even though the electron appears to be a particle, it's really a vibrating energy entity, what would be called a quantum field. And the way that this worked was there's actually a hole through the middle, so it forms a torus. The electron actually is a torus. And the other amazing thing about this was it's covered with blocks of information. So the electron is covered with these blocks of information. The blocks of information are constantly scanning the space around it in every which way. No one really knows yet how they're doing this scan, where that scan is occurring. But the end result is that if they detect a change, then they immediately react and do something. So for the electron, there was the issue of a so-called double slit experiment. When they shot electrons through one slit, the electrons went through as a particle. But when there were two slits that were close together and they shot electrons at them, then the electron all of a sudden turned into a wave and generated an interference pattern on the other side of the two slits. And the reason why that happens is because there's a scanning that's taking place here from this information, and the rules are that the electron can no longer behave as a particle. When it has two slits, it has to behave as a wave. Now, I don't know where that rule comes from, but I'm just telling you that's what's going on. Ron wasn't the first one to observe these subquarks. Annie Besant and Charles Leadbeater did this. And they published their observations in a book called Occult Chemistry in 1908. They had discovered in doing this that there were things called isotopes. That is that they looked at particular atomic elements, and each atomic element had an equal number of protons and electrons, so there was no net charge, but they had neutrons as well. And it was possible for the element to have different numbers of neutrons in its nucleus, and those are called isotopes. And so there's a mixture of isotopes that make up it's a weighted average of the nucleus weight that leads to what we call the atomic weight for each element. But what they missed here, what Ron discovered, was that there's dark matter subquarks, and they consist of 5 vibrating strings, not 10, and there's no charge associated with them. So they have no electric or magnetic attributes, and they just interact by gravity in attracting one another. But the thing that came out about the dark matter subquarks was the chemistry for them was entirely, again, a subquark chemistry. And Ron observed that they formed fern-like things, trees that were, incredibly dense, and so forth. So now, if we go back to where Western science has been for the last 50 years, they have this picture here showing here's an electron with 2 resonances, with 2 other particles here. I said that there were 3 holes in our matter subspace. So these 2 that are here are really a resonance from the electron. Similarly, there's a neutrino, and the neutrino has two resonances for the 3 holes. So there's really fundamentally only the electron and the neutrino. And then there are these, here they show quarks running around here, but Ron saw there were subquarks. There's at least 2 types of subquarks. Remember, they involve charge for matter and no charge for dark matter. So remember, this is all for matter. We have a similar thing for dark matter. And then there are these things called bosons that run around. But again, what these really are photons, and the electromagnetic field behaves normally. When you have electric charge, you have opposites attract and likes repel. So positive repels positive and negative repels negative, but positive and negative attract, except when you get very close to one another, and then it flips and the positives attract and the negatives attract, and you get what's called the gluon. So this is really a funny sort of photon that comes out of this. Similarly, there's a the notion of the weak force that's here comes about also due to photons. So all of these are just due to the photons. And the one that's funny here is we have a Higgs boson for matter and a Higgs boson for dark matter. They control the scalings, how much energy, how much mass is associated with everything that you see here in this picture. And so it goes. So that covers that. And this takes us down to what we need now for an extended standard model for matter and dark matter. We need matter fermions. So we have an electron and a neutrino. And then we have multiple types of subquarks. We have dark matter subquarks. Then we have the photon bosons here, plus two Higgs bosons, one for matter and one for dark matter. We have the quantization of space itself, spaces and compartments, and those compartments are in fact covered with blocks of information and also the algorithms that control the fields and forces generated in the matter and dark matter subspaces. And so something like this leads to a complete picture of a new standard model. We touched on this notion of information in the 1920s. We talked about this one slit, two slit experiments for electrons. That it was an incredible conundrum. And the physicist Louis de Broglie proposed that there was a pilot wave operating, and the physicist David Bohm, shown here, worked out an actual theory to explain this behavior of the waves and particles. Okay, the problem is no one has observed it other than Ron Cowan, and he did it in the 1990s. But the end result of all this is that this is an integral part of any sort of theory. There's a control mechanism that the information here will control the fields and forces that we see around us. So in particular, information is everywhere, and it's resonant in these Calabi-Yau manifolds in particular. And matter has a hierarchy where we start with physics at the bottom with the most fundamental things, the subquarks that are actually 10 strings vibrating, but there's also bosons and electrons. That in turn leads to the chemistry, which is electrons, neutrons, and protons running around, which in turn then leads to biology with DNA and RNA and so forth. So matter lives in this realm. In the dark matter realm, we just have 5-string subquarks. So we end up with a chemistry here of just these geometric branching trees, and the possibility that when there's a critical mass here of these subquarks, that they in fact become sentient or quiescent. Ron called them mind forms. Now, we're going to switch here to go back to the cosmology. We start with 1912, where Vesto Slipher, shown here, made observations with his telescope in Flagstaff, Arizona, that all the stars were moving away from one another. Edwin Hubble in 1925 had a much better telescope outside of Los Angeles, and he confirmed that this was indeed the case. And so that suggests immediately that if everything's moving away from one another, if you run time backwards, everything starts in the same point, which would have created a shock wave, a cosmic microwave background that would be still be evident today. And that was what the conjecture was. Where is that? That was actually observed in 1963 by Arno Penzias and Robert Wilson using this radio telescope shown here. Here's Hubble. So here's Wilson and here's Penzias, and here's the radio telescope behind them that was used for the Telstar communication satellite. And they had background noise in it that they could not reduce. And they approached Robert Dickey at Princeton, who had a theory that this was the cosmic microwave background from this Big Bang that was there. And many things have happened since then. I just shown here George Smoot, who carried out very detailed experiments with a satellite called the Cosmic Background Explorer. So he was above the Earth's atmosphere, being able to carry these observations out, and that led to all kinds of things. That here we see kind of three of these things. Here is the Cosmic Background Explorer in 1988 shown here. Here's the satellite, and it constructed this picture. Now, this picture shows the cosmic background radiation, but there was actually some crinkles in this. But the crinkles are shown in color to make them stand out. But actually, the peaks here are like just well under a hundredth of a percent. So effectively, this is all the same temperature, but not quite. There's some that are a little hotter, some a little colder than others in this background radiation. And then similarly, there was a different probe in 2001 called the Wilkinson Microwave Anisotropy Probe, and it constructed this picture, which showed even finer grain than this one here, as you can see. And then finally, there was a Planck Space Telescope shown here, and it constructed something here which was beyond what this is. So each of these things is confirming that there is this cosmic background radiation, and then it resulted in some crinkling of space, but this crinkling is very, very minor. Here is a graphic showing the Penzias-Wilson radio telescope, and if we tried to use the same picture, you'd see that everything looks, just on the same level. But when we go to the Cosmic Background Explorer, we end up with this picture here. And when we go to the Wilkinson Microwave Anisotropy Probe, we end up with an even better picture. So you can see the resolution increases from here. And here is the increase in resolution from the 1988, 2001, and then the 2013. You can see that, again, there clearly is some cosmic background radiation, but it's wrinkled in space. So this led to the following, that if everything is there at the start, is coming out of it, there's still a bunch of problems. One of them is that when we look at the sky, we see that everything looks the same in all directions, that this cosmic microwave background radiation is distributed evenly, and the stars that we see in the sky are also spread out, uniformly. We look this way, that way, the other way. We don't see a clustering of stars and then no stars. It seems to be smeared out. So what in the world could have done this? Well, the notion was shown here was at the very start here, when everything was rammed together, there was the space itself inflated, and it inflated over a very short period of time, from 10 to the minus 36 seconds after the bang started, to just 10 to the minus 32 seconds, say. So this is an incredibly short time period. There's an expansion of, say, 30 orders of magnitude of space itself. So Ron Cowan went into deep meditation, and he went back and looked, and he did observe, in fact, that space itself, the compartments of space were all compacted together, that they were filled up with dark matter. All of the matter had disappeared, had decayed, had washed out. So there was nothing but dark matter in these space compartments. And that then there was, in fact, this inflation that occurred, okay? But the key thing was he's doing this through deep meditation. There was no bang, okay? There was an inflation that occurred, that he saw, but there wasn't any nuclear fireball that went with it that was led to the notion of the bang. So this really was observed now to be a bounce, and that leads to a very different story. The notion of this inflation, by the way, you could think of it as the following, that if space is all compacted together, think of it as water here. And then all of a sudden it starts to evaporate. It starts to change phase into a gas. And so kaboom, everything just blows up into other areas. It's analogous to that. It's clearly not that. What Ron saw was the space compartments themselves physically expanded, 30 orders of magnitude. They had been all crunched together and then they went kapong. So what do we have here? Well, this big bounce hypothesis attempts to replace this cosmic singularity, which is the start of our universe, with a cosmic contraction and bounce. And so here's a graphic that suggests that. Here's our universe here, and it's bounced. You can see it growing, and then it contracts. So now here it is here. And then, hold on a second. And then there's another contraction, and then expansion. There's a bounce here, and then it contracts, and then there's another expansion and contraction, and so forth. And so this appears to be, this can explain everything that we see here. It includes the notion of inflation. There's a bunch of different things that come up. But one of the things that came out of the inflation theory was it suggests that there's multiple universes out there. We happen to be in one of them. And so if that's the case, then each of these universes is perhaps undergoing its own big bounce. So here's a bunch of universes. I don't know what you'd say is in between the universes. It's something. If this is the space that we have, this is the space for the in between the universes here. And these things are expanding and contracting and so forth. And so if this is the case, and there really is this cosmic microwave background radiation, and as we saw, Ron Cowan observed that there wasn't any bang here, there was a bounce that occurred. So all of this stuff in between here that led to a nuclear fireball till things cooled off and so forth gets replaced with what happened is perhaps another universe hit our universe 13.8 billion years ago. And when these two new universes collided, that created this cosmic background radiation that we see that is throughout our universe here. So we have to adopt what's called Occam's razor. The evidence is there. There really is cosmic background radiation. What is possibly the simplest hypothesis for explaining it would be there was no bang, but there was so after the initial bounce that occurred, our universe hit another universe and they merged. So this takes us back to this issue that Steven Weinberg, a Nobel laureate in physics, raised. Says one of the mistakes is is not that we take our theories too seriously, but in fact, we do not take them seriously enough. It's always hard to realize if you're a theoretician that these numbers and equations we play with at our desks has something to do with the real world. The most important thing accomplished by the cosmic background radiation measurements was to force theoreticians to seriously take the idea that there was an early universe. And here I'm simply arguing for Occam's razor. We take the simplest explanation to fit the available data. So we're going to push the envelope of our theories to come up with this. And therefore, our universe could very well have had its bounce trillions of years ago, but only 13.8 billion years ago do we have a collision with another universe. With that, we're done. And I want to thank you for your time. Any comments, please chime in and have a wonderful day.